to switch to the document cam, and we'll see how this is going to work. I appreciate the experimentation. Okay. I got to turn on more switches, more lights, more stuff. All right. So we got the document cam. So where we're at is in section 2.4. So we did yesterday, we started our erratic motion. Today we're going to be looking at things that are rocking and rolling, and we're going to be ending up with curvilinear. Okay, and we're going to do projectile motion and curvilinear motion. Couple of things. I don't know which calc book you had, Morgan, but for the calc book that you guys have either this edition or the later edition of this one, right? This is Larson, Holstetter, and Edwards.
I believe so.
Yeah. Chapter 12. Chapter 12 is where you kind of want to go back and look at, because this is our vector valued functions. Turns out in my ancient calc book, it's also chapter 12. It was like, okay, well, that's pretty cool. You know, the sequencing hasn't changed a whole lot in calc. So it's the vector valued functions, because you're going to be looking at integration of vectors, you're going to be looking at the differentiation of vectors, and if you remember, this is what was always funny, one of the groups that we talked about, normal and tangent vectors, and that's what we're going to ultimately get into today, are normal and tangent vectors. So we'll have those normal and tangent vectors. The projectile motion was in this chapter, the normal and tangent. But I also want to highlight for you guys, you're going to see almost the same types of stuff that you saw in calc under normal and tangent vectors, and then it's radius of curvature. So radius of curvature for you guys in this one starts talking about it in section 12.5. That we're going to be looking at arc length and radiuses of curvature and normal and tangent. So far we've been dealing with mostly linear motion, and we've been looking at different pieces, but now we're going to start looking over a curve. That curve can be a circle, that curve can look something like this, that curve can be an S shape. We're going to end up with a circle, but no matter what kind of curve we have, we can approximate it as part of an arc length of a circle. You know, we can actually look at those arc lengths of a circle, and we can actually play with that. Those arc lengths and those little individual sections are always going to have that circle associated with it. But if we go back and think about it in terms of general physics, when we were looking at our general physics, and I started with circular motion, we had an R, right? I have a position vector R. And I'm going to go along my curve here, and I'm going to do this as a little ds, right, or a change in s, depending on which way you're looking at it. And then I've got this one that I have out there, and this would be in our book's definition an r prime. We know we've got a position vector, and we know that our v average is just going to be our change in position with respect to time, and we can actually write our vector as dr dt. But one of the things that we knew about this, if I'm looking at velocity and I'm staying with velocity and I'm traveling at a constant velocity, one of the things that we knew in circular motion is if I broke off this circle, no matter where I went, my vector, my velocity vector, was always tangent to the curve. So we're going to be looking at tangent, tangent, and normal to the curves. And this became really important when we were doing circular motion, because if I was circular motion and I had my object traveling around here at a constant speed, this velocity, the magnitude of the velocity was the same, the magnitude of the velocity was the same, the magnitude of the velocity was the same. but I had a change in direction. And because these are vector quantities, that change in direction resulted in an acceleration. Because if I had a changing velocity, I had a change in acceleration, and we knew that my acceleration was going to be my change in velocity with respect to time, and I could do that as a derivative with respect to time, and then we also could get this as a d squared r with respect to time. And we had that change, and that gave us, this actually resulted in what we started talking about as centripetal acceleration. But this was, again, focused on primarily circular motion, okay? I was dealing with a nice uniform circular motion, and we had those pieces. And remember that r vector was going to be an x times my I hat, y times my j hat, z times my k hat. R was going to be my x squared plus y squared plus z squared. And we had a unit vector that's going to be my r vector divided by the magnitude of my r vector. So now if we're getting into vector analysis and doing the vector pieces of what we're after, I'm going to have dr dt is going to end up being the derivative of x I hat with respect to time plus my y j hat with respect to time plus my z k hat with respect to time. But let's look at just that component, okay? If I take my rules, I'm going to have a dx dt times my I hat plus a x di dt. That I've got, I can do that analysis. So this becomes dt. Now, this right here, if I'm in a fixed reference frame, right? I'm in a fixed reference frame. So x, y, and j coordinates are fixed, and I'm not dealing with anything else. This component is going to equal 0. Similarly, a dj dt is going to be a dk dt, which is also going to equal 0, provided that I'm in a fixed reference system.
What do you mean by fixed reference system?
My reference system's not going anywhere. So I'm sitting in this room, and my position vector is not going to change, okay?
So it's always going to be...
It's always going to be in this fixed reference. Now, I can put, okay, now here comes where we talk about relative velocity, right? I can be a fixed reference system inside the car on a train. But my train is moving. Okay? But if I'm working from the perspective of being inside the car on the train, I'm in a fixed reference system. I'm in a totally fixed reference system if I'm inside the car on the train. We deal with a fixed reference system all the time. We're sitting in this classroom. But what's the Earth doing?
It's spinning really fast.
And we're doing what else? We're revolving around the sun. So if I'm looking at us from a perspective of the sun, I'm not in a fixed reference system. But if I'm looking at us from the perspective of being in here in this room, I'm in a fixed reference system. So that's where one of these keys come in, and I'm pretty sure, haven't dug into it yet, because I'm staying about 5 seconds ahead of you guys. We're going to probably get rid of this assumption at some point, or there will be problems where we're going to have to get rid of that assumption. Now, it may not occur this semester, but when you get to graduate mechanics or dynamics, you probably are going to start to see it. Yeah.
Chemistry degree, usually it goes general chemistry, organic chemistry, then physical chemistry.
Well, because you're getting you're going into specific areas of that discipline. So, and the answer is it's sort of. Depending on where you're at, by the time I graduated with my physics degree, I had general physics or university physics. I had a 10,000 or junior level dynamics class, and when I got into graduate school, I had 3 other dynamics, classical mechanics, fluid mechanics classes. Yeah, it's really going to depend on your specific discipline. So, and the physics is always going to come into play with which area of physics. This is specifically just for mechanics, right? You guys are about to, the 4 of you in here are about to enter another area that you're going to look at electricity and magnetism specific to circuits. Okay, that's specific to circuits. There's a whole lot of electricity and magnetism that doesn't even come into circuits. You're looking specific to circuits. So that's where we end up and start playing with it. So what we end up with, that key point, is that my position vector with respect to time is going to look like Vxi plus Vyj plus Vzk. And we're going to introduce new notation. Okay? And Vy is going to equal y dot, and Vz is equal to z dot. Now this notation that we're using in this book, all of these are specific to the derivative with respect to time. So that notation is going to be that derivative with respect to time. Now we can take the next jump, right? I can take my derivative with respect to time, which is going to give me my acceleration. And now if I do my acceleration, which is going to be my dv vector, and I'm going to do the whole vector, it's going to be dvxi with respect to time plus dvyj with respect to time plus dvzk with respect to time, which gives us, making a similar argument, it's going to give us that A is going to plus AYJ plus AZK. And I'm going to have similar notation in that AX is going to be and I get that same piece. And remember, these are, and I'm going to show you a notation, WRT. I don't know if you've ever seen WRT, but it's a shorthand with respect to. Okay? With respect to. And that's with respect to time. And I'm going to be able to do the same order of magnitude and the same place. So we've got that new notation to kind of work with. So one of the key things that we're getting, hey, Morgan? I've been checking with Morgan. No. Did we lose her?
Isn't it always with respect to time?
No. No, and we're going to see that here in just a minute. So you didn't bring yours.
I can pull my laptop out.
Yeah, pull your laptop out because I think we've lost her because where did she go? Lost all due to poor connection. Interesting. Okay, well, okay, I'm gonna hang up and we'll call you. This Cade looks like he's trying to join too, so. Okay, you're back on. And Riley's on, because I've got two on. Somebody got a phone and text Cade, see if he can try again. Tell him to try and join via the Dynamics chat. And do you have something that you could text Jordan or chat with Jordan? Okay, see if he could try to get on.
I think you're the only one with kids. No, Kristen's got it.
We'll get the kinks worked out. I wonder if that glare is a little better. No, that's worse.
What is it, the screen?
However,
Just the screen, or is it like the whole view?
let's see if I get rid of this. Yeah, because that room is, because that's where the glare was really the worst. That might work better. Well, that might work much better for those seeing through my computer.
Yeah, I like that.
Huh?
I like that much better.
All right. So I got Jeremiah, that's good. We got a couple of them. All right. Okay. Now the big thing is I'm going to have to make sure I wiggle my mouse periodically.
You can change the settings on your, usually you change the settings and how long it takes.
Yeah, but it's when you get in here, it gets totally weird. I want to fill this up. Get a big screen here. There we go. All right. Okay. So if I have it on my book, well, that'll help me move it and keep this going. Okay, so now the big thing is, just like when we were dealing with circular motion. Oh good, that actually is showing up pretty nicely. Just like dealing with circular motion, one of the things that we had when this happened was because I had a change in direction, I got an acceleration. And that acceleration was center seeking. And as we looked at it, we also had a component where I had a tangential component. So I had those two pieces. So we can look at a unit vector for acceleration, where I'm taking my acceleration vector and I've got it with the magnitude of it. That we get it, that all the acceleration with velocity, everything was tangent to the path. But with acceleration, that no longer happens. We've got that center seeking part and we've got that tangent to the path. So this is where we're going to look at projectile motion, because projectile motion allows us to kind of look at it a little differently. So remember from projectile motion, and our book is using this kind of notation to give us our positives and negatives when we are writing different equations. We could look at our velocity with respect to this orientation, but when I was dealing with projectile motion, I have no acceleration in the x direction. So that goes away, and I just get my initial velocity, or my final velocity is going to equal my initial velocity in the x direction. And we could rewrite that, this one. But this one, that term goes away. And I could have the v squared terms And that term goes away, which just ends up being the same as that first one. And then we have the positive direction going up there, and I get my Vy is equal to V naught y minus my acceleration due to gravity, because we're dealing with projectile motion. And then I can have my y naught and then we could have this one, Vy squared is equal to V naught y squared minus 2g change in y. Now, this projectile motion makes a key assumption. That these only work if the Earth's gravitational field does not vary.
Does Earth's gravitational field vary?
Depends on
It can when you start moving away from the Earth, and it does vary even on spots on the Earth. Now, for most projectile motion over the space that what we're dealing with, again, this comes back to your frame of reference, for most of the time, it's not a big deal. When I'm kicking a football, does the gravitational field vary over the course of the football field? No. Now, if I'm on Mount Everest, is my gravitational field going to be slightly different than where I am now? Yes. But we do have a little, but if I'm playing soccer at the top of Mount Everest, do I have to worry about it? No. Now, we do know that the Earth's gravitational field is making it, but if I'm dealing with highly precise, now remember, significant figures, we're only dealing with 3 significant figures. So over the course of 3 significant figures, are we okay? Probably. But if I have a precision instrument that I'm trying to make sure is going to reach someplace else where I am going to have a varying gravitational field, such as sending out a probe into space, this assumption is not going to work. Okay, so we're doing okay. So we've got that piece there. So we do have that. So let's do a quick one. So I've got a ball and we've got a hill, right? So we've got a hill that's coming off. There's my horizontal. We're going to kick the ball off the top of the hill. We're going to have an angle of 30 degrees. And we're going to move in the X direction and we're going to move in the Y direction because we're going to end up down here at B. Turns out that my X direction is going to be 15 feet and my Y direction is going to be minus 9 feet. And what we want to do is we want to find the velocity when it hits.
Is that negative 9 feet?
Yes, because it's below my horizontal.
Okay, makes sense.
When it hits at B. So this is going to work just like our classic problem that we've done before. T, V naught xt, but that's going to equal V naught cosine of my angle T. So I can solve for T, right? I can get T is equal to 15. In the Y direction, I've got minus 9 is equal to V naught sine of my angle, because that's in my Y direction, T, minus, and these are in feet, so this is going to be minus 32.2 divided by 2t squared. Okay? And if I go in and plug my 30 degrees in, I get 15 divided by V cosine of 30 degrees. This is going to ultimately be 17.3 V, because I don't know V. I can substitute that back in and solve for V, and if I solve for V, I get 273.7, that's V squared, which means V is going to be 16.5 feet per second. I can solve for T at that point, okay? I can solve for T, and that's 1.049 seconds. So I can get my Vx, which is going to be my 16.5 cosine of my 30 degrees. It's going to give me my 14.3 feet per second. I can go back in and solve for my V. Let's do the Vy one. Vy is equal to, or Vy at B is going to equal V naught Y minus 32, minus 32.2 times time. And that's going to ultimately get me minus 25.5 feet per second. V is going to be the square root of Vx squared plus Vy squared, which is going to give me the square root of 16.5 squared plus 25.5 squared. And that works out to be 29.2 feet per second. So that one's not too bad, okay? That one's not too bad.
Which problem is that?
92. This
Wow.
this works out to be
Chapter
12. No, 12. We're still in chapter 12. We're getting close. We're getting really, really close.
90 what?
92.
Alright, thank you.
1292. I'm going to set up 1297 for you. Okay? I'm going to set up 1297 because there is a little bit different on 1297. It's a ski jump problem. So we got a ski jump with a velocity, and we are 4 meters from here. And then we have a slope, and it gives us the slope of 5, 3, 4, 5. And we end up down here at B, and this distance is 100 meters. So you start out at XA is equal to 0, and this is where A is, and that's where B is. YA is equal to 0. XB is going to be my 100 4/5, which is going to give me 80 meters. My YB, which is really kind of the trick to the whole problem, is I've got my 100 3/5 plus 4, and I end up at negative 64 meters. But it's going to work the same way as the other one, because if you're trying to find the velocity at B, you're going to work it exactly. You have to account for the fact that I'm 4 meters above where I'm starting down at the bottom, and I have to account for that when I'm in my Y. And my A becomes my origin point that I'm working with.
So let's just get X component by itself, Y component by itself. Solve for T or D.
You got to solve for V of X, V of Y,
Then find the magnitude.
and then find the magnitude at the end. And this one is 1297. All right. So here's where things get a little more complicated. So we're going to expand on the idea. So this section is a little bit on the projectile motion. We're going to start expanding on the idea. And we know that if I'm traveling around the curve, okay, if I'm traveling around my curve, I've got a component of acceleration that's headed inside, and instead of saying it's center seeking, like I do with circular motion, I'm going to call that normal to the curve. And then I'm going to have an acceleration tangential to the curve. Okay? And if I do that, and I'm looking at a velocity as well, my velocity can be written as the velocity, the magnitude of the velocity with a unit vector tangential to the curve. And that's just another way of writing my velocity. Okay? We also know that velocity is going to be my change in position with respect to time. So now let's take it one more step, and now my acceleration is my velocity with respect to time, but if I'm doing that with this component right here, I'm going to be taking this derivative with respect to time. I'm going to be taking that derivative with respect to time. I'm going to end up using my chain rule, and I'm going to get a tangential vector plus my velocity with respect to time, or my unit vector. That's respect to that. The question comes is, what is this? Because that's not something we've had to deal with in our problems before. Not had to deal with this. This has it has a direction change. Okay, it has a direction change. So let's look at my curve. So I've got a curve. I got some weird curve here. Okay, and we're going to look at it on this end. So I have some point of the center of curvature, and I can look at this as, we're going to use rho. So they were giving us a hard time yesterday about using rho. We're going to use rho because it's going to be kind of a script radius. And this is my initial rho. And I've got a unit vector that's tangential, and I have a unit vector that's normal along this. Now at some point along my curve, and I've drawn it bigger than what I would normally think of from a calculus point of view, I've got a new rho, and now I have a change in angle. So this is a change in angle, or a little incremental angle. I now have a new, and I have this increment right here, which is my ds, and we can do my And now, if I look at it and kind of play with it, I can say that this now is something that looks like that, where this is my normal vector. So my u tangential, dot tangential, ends up being my change in angle with respect to my normal vector, which is now an s divided by a rho times my normal vector. And this now is a v divided by my rho times my normal vector. And so I end up with an A that looks like this. I get an A tangential with a normal vector, and we end up with AN ultimately ending up looking at V over rho. And we've seen that before. We've seen that one before. If it's circular, right, if I'm doing circular motion, we've seen that one before. That's my centripetal acceleration, and my centripetal acceleration is V squared over R. The key here is I'm now approximating little sections of my curve as circles. And I'm following those little sections of my curve as circles. And so I also can get, which we've also seen, that this ended up as the square root of my tangential component plus my normal component for my vector for A. Okay. So now let's think about it in 3D. So now I have a plane, okay, and I've got something that's traveling across the plane. And so this will have a center of curvature here, All right, so I have a center of curvature here, so this is gonna be my unit vector tangential. This is my unit vector in the normal towards that radius of curve. The third dimension, I'm gonna have another unit vector that's gonna come up here. We can call it u of b. And then u of b is equal to my make sure I get it right, ut cross product un. Which we've seen in physics when we started dealing with the motions of electrons and start dealing with how the waves, we started getting into those, looking at our cross products, looking at the motion. When we're dealing with a magnetic field or an electric field, we started seeing, well, where does my particle go if I've got, the magnetic field or the other field playing with it. So we see this before from that perspective. This problem and get you started so that you can actually see what you might be encountering when you have the number. This one, so I'm starting at A and I've got a train that's following a curve. And this is point A, and we've got my little train sitting here, my little Dr. Seussian train, and this is 400 meters. And this curve is going to follow that y is equal to 200 e to the x divided by 1,000. Got e to the x divided by 1,000. And we're told that at A, the velocity is 30 meters per second. And then we're going to start decreasing with the speed, decreasing the speed with a constant acceleration of minus 0.25 meters per second squared. We want to determine the magnitude of the acceleration at B. This is our B. And we're also told that this change in S is equal to 412 meters. So the path that we followed is 412 meters, but we've moved 400 meters on the x-axis. So I can find the velocity squared at B is going to equal my velocity squared at A plus 2, the acceleration tangential, times my change in position.
That looks like a kinetic equation.
It is.
It is, but it's just with a difference of.
Yeah, it is. It's the same thing. It is. So this is going to be my 30 meters per second squared plus 2 times my negative 0.25, and my change in position was 412.
Is that an A sub t?
Yep, it's the tangential acceleration. This is my tangential acceleration. If I do the arithmetic, I get VB is equal to 26.34. Because, in this case, my normal acceleration, right? My normal acceleration is going to be the velocity squared times this radius of curvature. Because I'm going up that curve, right? That radius of curvature. Hence, I went back to the calc book to look at how does one calculate a radius of curvature. Because guess what? Our dynamics book does not give us that particular piece of information. It talks about radius of curvature, right? Right? So it talks about radius of curvature, but I got to find that piece out. So let's look at it. So what we're doing is when we're traveling down a path, we're taking each segment ds of the curve is formed from an arc of an associated circle And that circle has a radius of curvature, or rho, and a corresponding center of curvature, O. So that radius of curvature comes into play. And you can go back to your calc book and you can find that the radius of curvature, we can do that. It's 1 plus the derivative of y with respect to x squared, 3 halves, divided by, and this is the absolute value, and we're given that y is equal to 200 e to the x over 1,000. So dy dx is going to be 0.2 e to the x divided by 1,000. dy is equal to 0.2 and I can plug all that stuff back in to that. And then I want to evaluate it at 400 meters. Because point B on the x-axis is 400 meters. And when you put 400 meters in that spot, you get that the radius of curvature, I calculated it to be 308.12 meters. The book calculated it to be 3,808. My guess is it's just a significant number of significant figures that they're carrying through the calculation. Because when you ultimately come in and you calculate the acceleration, it's going to be my tangential one. My tangential one was minus 0.25. The normal one acceleration normal ends up being v squared over rho, which is my 26.34, which came from that first part, squared divided by my 3,812, gives me 0.182, and that's in meters per second squared. A becomes the square root of my 0.25 negative squared plus 0.182 squared, and you end up with 0.309 meters per second squared. And that's exactly what the author gets as well. So I'm pretty sure this difference between the 3,812 and the 308 is just the number of significant figures that I carried through my intermediate calculations.
Isn't that like pretty much negligible at such a big number?
It could be, but it may not be. It may make me miss that asteroid.
It may what?
It may make me miss the asteroid.
Oh.
Because if you think about it, think about this. You know, let's talk about that for a second.
Let the gravity suck it.
Well,
Asteroids not that big.
look at what happens. If I'm off by 0.1 degree, and I'm over here, that line isn't all that big. But when I'm over here, it's big. And if the object I'm trying to hit is like that 0.1 could make me miss it. You know, and in this case, what we're doing right now is just working through why we're working the problems and how we're using those methods, and that's really the key. It's showing you the methods that we're doing, and some of the underlying, because the underlying physics is the same that we've been dealing with. We haven't learned any new physics. All we're saying is that, in general, in engineering physics, I disregarded what happens when we're traveling around an ellipse. versus a circle. Now we're saying, well, it's not even an ellipse now. It's some sort of weird roller coaster curve. Right? You know, think about what we've been doing. We had simplified things, and the same thing we did in statics, right? We started with one-dimensional things. Then we went to two-dimensional things. Then we went to three-dimensional things. Well, we're doing the same, thinking that, well, you can't really approximate it as a circle anymore. Or in an infinitesimally little small space? That's going to be hard pressed. If I'm the little particle that's traveling on that thing, it's going to be hard pressed for me to say I'm not riding on a circle. It's going to be really hard pressed for me to do that. That's why we're actually working with. This gets us, just so you guys know where we're at in the book. What we have left in chapter 12 is not a whole lot. What we have left in chapter 12, systems. So far we've stuck in X, Y, Z. So we're going to look at those equations in the other coordinate systems, like cylindrical coordinate systems. And then it gives us, so that's the cylindrical coordinate system. And then we're going to start looking at some machine portions and looking at how that works. And a little bit of relative motion, and then we're done with chapter 12. Now I went ahead and get to rigid bodies. We're building off of this. So rigid bodies is going to go a little bit faster. We're just going to have to take into account that now I have to worry about the motion of the body. This we've only stuck with particles. So I think we're going to be able to get us where we need to be all the way. I wanted to, kind of lay the groundwork of where we're having to talk notation. We're having to talk, you probably want to keep your calc book kind of handy. We're having to talk about calculus that you're going, why on earth would I do this? Well, the reason is because we're actually going to ultimately apply it in terms of our dynamics. And that gets us, like I said, I'll be working some of these problems, and then we've got kind of the summary, and I do like the chapter reviews, and then we've got the review problems, and then we're starting to look at forces in motion. So tomorrow my plan is to work a lot more problems, and we'll probably work them in terms of the circular motion, because basically we'll have to dive into a little bit on that relative motion, but we're getting to the point of just kind of working some more problems. So you guys on the Skype, how's it going? Okay, and you guys can see the screen pretty well? Great. I think this is going to work, guys. I think we're going to make it work. Yay! I'm stoked because when we get Zoom on campus, we're going to be able to do a lot more things, and so I really thanks for you guys checking in. I'll get this posted because I'm not going to do much more today because I got a meeting I got to run to, and I'll get this one posted, and we'll work problems tomorrow. And we've already cranked through some material.